In the late 1950s and through the 1960s, engineers on both sides of the Cold War were solving the same problem from different directions. How do you preserve structural timber inside an underground facility that must remain operational for an indefinite period without the access required for routine maintenance? The constraints were unlike anything civilian construction had faced. There was no provision for returning to a sealed facility every 5 years to recoat deteriorating surfaces. There was no budget line for replacement when preservation failed. There was only the requirement that the structure remain intact and functional from the day it was sealed until the day it was needed, which could be next year or could be in 30 years, and the preservation system had to perform identically in both scenarios. The solutions that emerged from that requirement have been largely declassified over the past 3 decades, and what they reveal is a systematic approach to wood preservation that civilian construction has never adopted, not because it does not work, but because civilian construction operates under a different economic model where periodic replacement generates ongoing revenue and maintenance is expected rather than designed out of the system. When the economic incentive for maintenance disappears, the engineering approach to preservation changes fundamentally. The organizing principle of the Cold War underground preservation system was layered redundancy, the same principle that governed every other critical system in those facilities. A single point of failure was unacceptable in the communications array, in the air filtration system, in the power supply, and equally unacceptable in the preservation system that protected the structural timber those systems depended on. Each layer of the preservation system addressed a specific failure mode. Each layer provided protection for the layer beneath it against the failure mode it could not address on its own. The system as a whole was more durable than any of its components because the failure of any single layer still left multiple functional layers between the wood and the conditions that would destroy it. The outermost layer addressed bulk moisture, the direct infiltration of liquid water through the wood surface. The material requirements for this layer were specific and non-negotiable: impermeability to liquid water, flexibility sufficient to accommodate timber's dimensional movement with temperature and humidity changes without cracking, and film integrity continuous enough to span the surface irregularities, joints, and gaps that are present in any structural timber assembly. A coating that cracked under thermal cycling concentrated moisture infiltration at the crack location and effectively negated the protection across the entire surface by creating a high flow pathway. The bituminous materials selected for this layer, coal tar derivatives initially, modified bitumen compounds as the chemistry developed, met all 3 requirements simultaneously. Their viscous, semi-plastic nature bridged irregularities. Their flexibility under stress prevented cracking. Their impermeability to liquid water provided the bulk moisture barrier the outer layer needed to be. BXISBS modified bitumen waterproofing membrane brings the material science of that Cold War outer layer into a modern format that is practical for non-industrial application. The SBS polymer modification, styrene butadiene styrene, the same rubber-like compound used in high-performance roofing and below-grade waterproofing, gives this membrane the flexibility and self-healing properties that simple asphalt alone cannot achieve. Applied to timber that needs a continuous, durable, flexible outer moisture barrier, structural members in ground contact, below-grade framing, or any wood surface in a high-moisture environment where maintenance access is limited, this is the material that creates the outer defensive layer correctly. The Cold War engineers did not have a better product. They had a better understanding of why that layer had to be right before anything else mattered. The link is in the description. Coverage consistency was the variable that determined whether a multi-layer system performed as designed or failed at the hidden gaps that uneven application always created. Cold War engineers identified brush and roller application on complex structural geometry as an inherent source of coverage failure. The tools that worked efficiently on flat surfaces consistently left thin spots at joints, corners, undersides, and recesses, and those thin spots were where moisture found its pathway regardless of how well the visible surfaces had been coated. Industrial spray systems solved this by delivering material to every accessible surface simultaneously at a consistent film thickness that did not depend on the applicator's angle, reach, or attention. The Von Forn 700-watt HVLP sprayer gives you the same coverage consistency on complex wood geometry that those industrial systems provided. 4 nozzles, 3 spray patterns, easy clean design, the tool that eliminates the hidden coverage gaps that make a multi-layer system behave like a single layer one at the worst possible location. The link is in the description. Underground timber preserved according to this system in the 1960s is still intact. Not because the materials were exotic. Not because the conditions were favorable. Because the system addressed every failure mode systematically and applied each layer with the consistency required to make that layer actually function. Applying the same logic to your own projects does not require Cold War budgets or industrial equipment. It requires understanding what each layer needs to do and using the tools that allow it to do it correctly. Subscribe to In the Beginning. The product links are in the description. See you in the next one.